Hello everyone. Welcome to the next lecture on the real analysis. Today I will explain you the concept of uniform convergence. Myself Dr. Harish Garg. You can follow my YouTube channel where you can find the playlist of real analysis, and you can see that the last lecture was on the pointwise convergence, Cauchy criteria, and the various examples of the pointwise convergence. Apart from them, you can also see the various lecture related to the sequences and the infinite series available in this playlist. You can subscribe my YouTube channel so that when I uploaded my next video, you will get the notification. So what we have discussed in our last lecture, that we have described the concept of the pointwise convergence for the sequence of the function. That means if you have the sequence of the function fn defined on the domain A to R, where A is the subset of the R, then this sequence of the function is said to be the pointwise convergent when you can say this fn is convergent for each x belongs to the A. Remember the concept for the each x belongs to my domain. Now, in this lecture, we will see what are the stronger form of the pointwise convergence. That means we are talking about the uniform convergence. The difference between the pointwise and the uniform convergence is similar as of the continuity and the uniform continuity. So I will explain you also in this lecture what is the basic difference between the pointwise and the uniform convergent. Now remember student, the most important thing is the definition of the uniform convergence. You must write down this definition on your copy so that when I use this definition, the various slides, you will able to understand easily. Suppose fn is a sequence of the function which are defined from the A to R, then fn is said to be convergent uniformly on the A, where f is also from the A to R. If for a given epsilon greater than 0, we have fnx minus fx is less than epsilon. Remember, it is for all. This is for all. However, for the pointwise convergent, instead of the for all, it is for the each x. Fine. So that's why I'm asking you, don't forget to write this definition on your copy. Remember that in case of the uniform convergence, this value of the m, which is a part of the positive integer, is dependent only on the epsilon. However, in case of the pointwise convergence, this m dependent on both epsilon as well as x. If you look about this definition graphically, how you can say for the graphically? So look at that. If I just draw the graph of the x and y, what is my domain? A. So A is a subset of the R. So I consider this is my A. That is a subset of the R. Then I can assume, say this is any graph of fnx. Find sequence of the function, because I have defined on the y-axis, I call as y is equal to fnx. Fine. Now look at that. We need one more f. So I can consider, say this is my f. Y is equal to fx. Fine. Now when this function is said to be the uniform convergent, if you look about this definition, can I write this definition to be this form? Fnx minus fx is less than epsilon. Fine. So can you find the value of the fn? So that will be fx minus epsilon is less than of the fnx is less than of the fx plus epsilon for all x belongs to my domain. So that means if we are able to draw fx minus epsilon, so epsilon can be any positive number. This black color is my fx. So if you draw the graph of the fx minus epsilon, this is my fx minus epsilon, and similarly this is my fx plus epsilon. Fine. So below part is my fx minus epsilon, upper part is my fx plus epsilon. If inside this domain capital A, if inside this domain fnx is lies between fx plus epsilon, fx minus epsilon, and you can see that in this graph the value of the fx will be this blue, this color. You can see this line is lies in between the dotted lines. Fine. What is the dotted lines? fx minus epsilon and fx plus epsilon for all the domain. Then you can say fnx converges to the fx uniform. If for inside the domain, if for some cases fx lies outside this domain, then it is not uniform convergent. Always remember student, the if fn converges to the f pointwise, fine, and fn converges to the f uniformly, then this f and this f are always same limit. Moreover, if fnx converges to the f uniformly, this implies fnx converges to the f pointwise. However, converse may not be true. Now, how you can check about the uniform convergent? Whenever you are asking you check whether the sequence is uniform convergent or not, you need to check about the 2 points. The first one is you need to check about the pointwise convergent, and then you have to check about the uniform convergent. So what we have discussed in the pointwise convergent, we need to find the limit of fn. Fine. If this limit exists and unique, fine, if this limit exists and unique, then you can say it is a pointwise convergent, otherwise not. If the sequence is not pointwise convergent, then it is not uniform convergent. However, if the sequence is pointwise convergent, it doesn't implies that it is pointwise convergent. But if it is not a pointwise convergent, this implies it is not uniform convergent. Now, first method is first way you have to find the pointwise convergent. Then how you can check about the uniform convergent? We have the two different methods. The first one is by the definition, that is fnx minus fx less than epsilon. Second method is known as the MN test. In this lecture, I will try to explain you the concept of the method 1. That is how you can check about the uniform convergent by using the definition 1. Now, look at this one particular example. So, show that the sequence is not uniform convergent. So, first way is you have to prove that it is not piecewise continuous. Then it is easily proved that it is not uniform convergent. Second is, if you prove that it is a piecewise convergence, and if you prove that it is not a uniform convergent, then it satisfied this statement. So what is my target? Given that fnx is my this case, your target is to find pointwise convergent and uniform convergent. What is the concept of the pointwise? Your target is to find this limit. Now clearly say for all x belongs to the R, clearly say if x is my 0, this limit will be 0. If x is my non-zero, this limit will be my non-zero. So we have the two different cases. The first case is x is 0, x is non-zero. If x is 0, what is the fnx? Fnx is my 0. So therefore, what is the value of the fx? That is limit of the fnx. Limit of the fnx is my 0. So therefore, fx is also my 0. When x is non-zero, then what will be your fnx? It is my nx divided by 1 plus n square x square. Then your target is to find the limit. Now clearly say it is infinity by infinity form. So I can apply the L'Hopital rule. So what is the L'Hopital rule? With respect to n, you have to differentiate this. Now clearly say x is my non-zero. So this limit will be my 0. This is the first method. There is one more method. You can divide the numerator and denominator by n square. So it will be x over n, 1 over n square plus x square. Now clearly say when you take n approaches infinity, numerator will be 0. 0 plus x square is my 0 because x is my non-zero, so it is my 0. Fine. So therefore, fx will be 0 for both the cases. Hence, it is my pointwise convergent. For more detail about the pointwise convergent, I recommended you can watch about my this lecture example of the pointwise convergent. Anyhow, Now since you have the two cases, x is 0, 0 and then so. Now down the come on the main point is the uniform convergence. Your target is to show this one. Since my pointwise convergence has the two cases, so for the uniform convergence we also consider the two different cases and try to find out this value. So what is the value of the fnx minus fx? When x is 0, fnx is 0, 0 minus 0 is 0. In this case, what is my fnx minus fx? Fnx will be my nx divided by 1 plus n square x square. Fx will be my 0. So the answer will be nx, because x is my real number, it can be positive or negative, so it's n more. So I can substitute this value at this point. Fine. And remember, your target is to find the value of this m. Now I can cross multiply this. It will be n mod x less than epsilon plus n square x square epsilon. Fine. I can write on this right hand side and I can put this equation. So you can easily say your target is to find the value of the m. That means it is quadratic in n. So once is a quadratic in n, you can find the formula like b square minus b plus minus b square minus 4ac over 2a. So this is my a, b is my minus of mod x, it will be. Now whenever you are trying to find the n, then you can see that your target is n is greater than or equal to m. Always consider the two case. Fine. The first case is, can you find the value of the x? Can you find the value of the x so that this limit will goes to the infinity? Fine. Second case, can you find the value of the x so that it does not goes to the infinity? So can you find the value of the x from the domain so that this becomes infinity? Yes, clearly say whenever x approaches to the 0, because it's a denominator x. So whenever x approaches 0, you can see this value will go to the infinity. So that means this number n is my greater than infinity. Can you find the value of the m? Can you find the value of the m such that n must be greater than or equal to m? No. Fine. So that means you are unable to find the value of the m so that this equation will be satisfied. So therefore you can say 0 because x approaches 0. So 0 is my point of non-uniform convergence. Fine. So what is the point of non-uniform convergent? All those points at which this condition does not hold. Now this is a case 1. When x approaches 0, then it will be infinity. While for all other x, whenever x does not approaches 0, this limit will always be the finite. So then we can easily find the value of m. Hence, this sequence is not uniform convergent on any interval which contains 0, like -1 to 1, -3 to 3, -3 to 7. Fine. So if you consider this sequence and intervals are either one of them, then it is not uniform convergent. However, if you consider this interval, because 0 does not belong to this, then it is a uniform convergent. Look at this another example. Show that the sequence converges uniformly. Again, your first target is to check the pointwise and uniform. So for the pointwise, we need to find this limit. Now you have the closed interval. So I can take the three cases. X is equal to 0, x is equal to 1, and x lies between 0 to 1. So what will happen if x is equal to 0? Then your fnx will be 0. So then your limit will be 0. If x is equal to 1, then your fnx will be 1 over n. Then your limit will be 0. When x lies between 0 and 1, then what will be your limit of fnx? That will be limit x raised to power n over n. Now clearly say whenever x lies between 0 to 1, x raised to power n will be 0 over n. So as n approaches infinity, this is again 0. So you can see in all the cases, the limits is my 0. Fine. So it is 0, it is 0. Fine. Hence, you can say the function fn converges to the 0 pointwise because the limit exists. Now consider the case of the uniform continuous. Again, you have the two cases, or since in each case x lies between 0 to 1, fx will be my 0. So therefore, what is the value of fnx minus fx? It is x raised to power n over n. Because x lies between 0 and 1 is a positive number, so I can write this is simply x raised to power n over n. I can substitute this value in this equation and you can find the value of the n. So it will be x raised to power n is less than of the n into epsilon. Fine. How you can find the value of n? I can take n is my greater than of x raised to power n over epsilon. Now again the two cases, can you find the value of the x so that this limit will go to the infinity? This limit will go to the infinity only when x will be infinity, but my domain is 0, 1. So that means this limit will not go to the infinity. So once that means the first case is not applicable, then we are working on this second case. So then whenever this limit will be the finite, you always try to find the maximum value. How you can find the maximum value? Clearly say this will be maximum only when x will be maximum, because x will rise in the numerator. So what is the maximum value of the x? That is a 1. So what is the maximum value of this? 1 raised to power n over epsilon, that is 1 over epsilon. Fine. So that means you can say m must be greater than of the 1 over epsilon. So we can choose an integer which must be greater than of this, and it must be greater than of x raised to power n over epsilon. Fine. So therefore we can say this is result is true for all x. Hence fnx minus fx must be less than epsilon for all n greater than equal to m. Therefore fn converges to the 0. Why 0? 0 is my fx. Because fx is my 0, therefore fnx converges to 0. Look at one more example, which is a combination of the first and second example. I hope you can like and comment on this video as well. Okay, check. Show that the sequence is uniform convergent on A strictly greater than 0, but it is only pointwise convergent on the closed interval 0, b. Fine. Again, your first target is to check the pointwise and the uniform convergent. Can you find this limit? So what is the domain is? For the pointwise convergence, so I can consider the case x is equal to 0, I can case x is equal to b, and I can take in the case x lies between 0 to b. When x is equal to 0, what is my fnx? E raised to power 0, 1. So can you find the limit? Limit of the fnx will be my 1. When x is equal to b, what is my fnx? Fnx will be e raised to power minus n into b. Then your limit of n approaches infinity, it goes to the 0. Whenever x lies between strictly 0 and b, then your fnx will be e raised to power minus nx. Again it goes to the 0. Fine. So that means whenever x is 0, it is 1. Otherwise it is my 0. Or I can combine these two cases. I can written like this manner also. Fine. So when x is 0 or x is greater than 0, or you can also say x is fine. So this answer is my 1, this answer is 0. And you can see this limit is existence. So therefore fnx converges to, this is my f, converges to the f point wise. Fine. So you can see that this part is satisfied. Now you can see about the uniform convergence. Again, you can see there are the two cases. So we can take x is 0. Second is x is greater than 0. So then your target is to find this value. When x is 0, what is the e raised to power nx? 1. What is the fx? 1. 1 minus 1 is 0, which is definitely less than epsilon. Look at this case, when e raised power minus nx, whenever x is greater than 0, it is my 0. So I can substitute this value of the fnx minus, this is 0, and this is e raised power minus nx. Can you find the value of the n? How you can find the value of the n? I can take the logarithm on the both side. Fine. So then n will be greater than of minus log epsilon divided by x. Fine. Or I can replace minus log epsilon to be log of 1 over epsilon divided by x. Fine. Now again you can see there are the two cases. Can you find the value of the x on this any interval a comma b, where on this interval, so that it goes to the infinity? Yes, clearly say x is equal to 0. Fine. So that means whenever x approaches 0, this limit will goes to the infinity. That means there does not exist any m, or we can't choose any m such that this condition hold. So therefore you can see the sequence fnx is not uniform convergent for any interval which contains 0. Fine. So that's why he said that a is strictly greater than 0. Now that means we are talking about the second case. Fine, this is the case 1. Then we have to find the second case. You have to find the maximum value of this. So because 0 is the point which is non-uniform, so called as this one. Now how you can find the maximum value of this? So how you can find the maximum value of this number? Clearly say the maximum, because this quantity is my constant, so the maximum value will be dependent on this 1 over x. So what is the maximum value of this? This will be maximum when x will be minimum. So what is the minimum value of this interval? The minimum is my a. So what is the maximum value of this quantity? The maximum value of this will be my 1 over a log of 1 over epsilon. Fine. Because we need a maximum value, and maximum value will be occurring corresponding to the x component, and x is written in the denominator, so that means the minimum value of the x. If the function is given like this manner, then what is the maximum value of this? The maximum value of obtained as corresponding to the maximum value of the x. So maximum value of this will be my b log of 1 over epsilon. Fine. So anyhow, in this case there is only the maximum value occurring at 1 over a log 1 over epsilon. Therefore we can choose an integer m which must be greater than of this, and which must be greater than of 1 over x log 1 over epsilon, because this quantity is my maximum value of this function or this sequence. Then we can say this. Therefore fnx minus is true for all x belongs to the a comma b, provided a is my non-zero. Hence the sequence is convergent only on the interval which satisfied that this is non-zero, like 0.00127, or you can also say open interval 0 comma infinity. Fine. Or no, it's a closed interval, open interval 0 to 7, open interval or closed interval 1 comma 9, or anything. So this function is uniform convergent on this one. So for more detail you must watch about my this Cauchy criteria for uniform convergence and examples of the pointwise convergence. We will see more examples on the uniform convergent in our next lecture. Till then you can see and watch my YouTube lectures. Kindly like, share and comment on this video. Best of luck students, and don't forget to subscribe my YouTube channel. Happy learning always. Best wishes.